Now, we're able to combine the elements we worked with before, capacitors and resistors. Now we can see the capacitors, the effective capacitors will change over time because as the charge builds up on the capacitor, it'll impede the flow of current through that capacitor such that, if I were to close switch 1 right here and leave switch 2 open, then initially, I'd have an electron that runs around here, sticks onto that side, knocks an electron free on the other side, continues around, and I would build up negative charge here and positive charge here until such time as the change in potential over the capacitor would be equal to the change in the potential over the battery. And there would not be any further current flowing. Because then the change in the resistor would be 0. I'd have here, let's see, S1 closed, T equals big, delta V over the capacitor will be equal to the EMF in the opposite direction. So the potential over the resistor will be 0. Now, let's look at some of the steps of that over time. And let's start with the idea that I close switch 1. Now, I have from the loop equation that the EMF of the battery plus the change in potential over the capacitor. Okay, this closes. I've got one battery driving things, so I'm going to define the current going from positive to negative in the battery. Then the potential over the resistor, well, the potential will drop by I, R1. I get back to where I started. The change in the potential is equal to 0. Now, tell you what let's do. After some long period of time, then I've got these cases end up, and the current will go to 0. So the current at time t equals 0 is the highest it's ever going to be. Because the first electron in our Timmy the electron model doesn't even appear to slow down. So that starts at its highest value of, well, from Ohm's law, delta V equals IR. That starts off as the EMF of the battery over the resistance of the resistor, and as time goes to some big number, it goes to 0. So, let's look at the other case where, I think the red one might be showing up a little bit better. Switch 1 is then open, and switch 2 is closed. So now we open this back up, and we've got a hole in our path, so there's no path for the current to move through, so we're stuck. We take it through here, and I've got, okay, and now that's closed. So what can happen here is that the electrons on this side can move through the wire, through the resistor, and fill those electron holes on the other side, giving us a current as drawn, such that if I take that and I take a loop equation over that case, then I've got the change in potential over the capacitor minus the current times the resistance is going to be equal to 0. Okay, unfortunately, I need to write these in the same terms because the change in the, I can write the change in the potential over the resistor in terms of the charge on the resistor at any given time. And I'm going to go to a lowercase letter here because it's a parameter that can change. Typically we use like the uppercase letters for this is that thing. If it can vary with time, we'll typically use a lowercase letter, for less emphasis. Now, minus I times R, but I've got Q varying over time and current varying over time because the current will start at a high value, but the current will die to nothing as, in this case, the charge spreads back out. Happily, I can write the current as the change in charge over the change in time. And actually that's using, we're just keeping those on the same side right now because we will get together and I can rearrange this equation. From Q over C is equal to negative dQ times R dt. I can rewrite this as the change in time over RC is equal to negative, or let me take the negative sign over as well, negative dt over RC is equal to dQ over Q. Now, if I integrate over Q, the integral of 1 over Q dQ is equal to the natural log of Q, and this is, then if I integrate this over Q and integrate this over T, then from 0 to Q, and that's from 0 to some time T, then I'll have minus T over RC. Now, I want a function of Q in terms of everything else. So I want to get rid of this natural log. So if I take both sides and raise them to the power of e to the natural log of Q is just Q is equal to e to the minus T over RC. So the charge will vary exponentially with time. And by going through some of these limits, by setting up the limits quickly, I kind of flew through them here, then the charge over time will start off at its maximum value, the maximum value Q stored on the capacitor, and that will decrease with time where there's a time constant tau equal to the resistance times the capacitance, and if you work that out, that has the units of seconds. So, I have that the charge on the capacitor as a function of time is equal to the maximum charge times e to the minus t over tau. the change in potential over the capacitor starts off at its maximum value and also decreases over time. And if we were to go through this in this behavior when we're starting up, we would find in a similar fashion when switch 1 is closed, the current will start at its maximum value and decrease with time. And the potential over the capacitor and the charge on the capacitor will start at 0 and increase to their maximum values as time goes on.